Hi everybody, my name is Florian Gallet. I'm from the Geneva Observatory, and today I will present you the work I've done about the impact of the evolution of the stellar parameters on the habitable zone limits and the possible use of these results to constrain at the zeroth order the planetary habitability. So a little context. Nowadays we know more than 2,000 planets that have been confirmed and that are in a wide range of different configuration of planetary and stellar mass, radius, distance from the star, and so on. Among these 2,000 exoplanets confirmed, about 30 of them are believed to be inside the habitable zone of the star. And this number will dramatically rise in the future thanks to the Kepler, K2, and the future Plato mission. But being in the habitable zone didn't imply for the planet to be considered as habitable. So what are the required conditions for planet to be habitable? And is surface liquid water the only criterion? We already know that the answer to this question is no, okay? But what about stellar and orbital evolution? The habitable zone is not a snapshot, even though the habitable zone is often estimated at the age of the star-planet system. But the habitable zone will follow the intrinsic evolution of the star. Moreover, the planet will not remain at the same location for the whole stellar evolution, okay? So you need stellar models. In this work, we used the stellar structures evolution model Tidal that is developed in Geneva, among others by Louis Amar, Corinne Charbonnel, and collaborators. With Tidal, we can follow the main features of the star: the radius, the mass, effective temperatures, luminosity, internal structures. Tidal also include a full self-consistent treatment of rotation, so we are also able to follow the surface rotation as well as the internal profile of this rotation. For the habitable zone here, we used the prescription of Casting et al. 1993 that express the habitable zone limits as a function of the luminosity of the star and as a function of this quantity SF, that is the stellar effective flux, defined by the ratio of the infrared flux produced by the planet to the flux received by the planet from the star. This quantity comes from a climate model. We use here an updated version of this climate model from Casting et al. 1993 by Koparapo et al. 2013 that express this quantity as a polynomial expression of the effective temperatures, with this quantity here that depend on the planetary atmosphere. For the habitable zone limits here, we use for the inner edge the runaway greenhouse limits. So basically what does it done is that they start with a fully saturated vapor atmosphere, and they increase the surface temperatures of the planet. So here you have an increase of this quantity SF, because here you have the absorption of the infrared flux by the water. Then at some point the atmosphere becomes opaque to this radiation. This is called here the moist greenhouse limit. And beyond 2000 Kelvin, you have the atmosphere that will, the surface of the star and the lower atmosphere will start to radiate invisible in near infrared flux. So you have SF that here increase again. And this point here is called the runaway greenhouse limit, because here at that point you have the greenhouse limit that start to run away. So you will reach very high temperatures and eventually all the ocean are evaporated. For the outer edge, we use the maximum greenhouse limits. So they start with N2 based atmospheres. They increase the CO2 partial pressure. So first you have the decrease of the effective stellar flux because of the Rayleigh scattering, because of the CO2 compound. You decrease the SF. And at some point here, you have the infrared flux that start to plateau, okay, because of the Rayleigh scattering of the CO2 compound, while you have the absorption of the near infrared flux that continue to decrease. And so after this point here, you have SF that start to increase again. So you have the outer edge move outward and then start to move inward again. And this minimum here is define what we call the maximum greenhouse limits. Okay, so this is the two regions that we are looking for. These are the different prescription and stellar features that we studied. So we start with the habitable zone prescription. Here we use the Kuparov et al. 2013. We compare it to Celsis et al. 2007 and Darwood et al. 2003. These three prescriptions are based on the climate model from Casting et al. 1993. So this is why you have something that is quite similar. This figure here shows the distance from the star in astronomic unit as a function of age. Here you have the different stellar evolution phase. So here you have the permanent sequence phase with the Hayashi NEA track. Here you have the zero-age main sequence, the main sequence, and then the red giant branch of the star. So as you can see here, there is no effect of the prescription on the evolution of the habitable zone limits. Okay. Now, different stellar models. Such analyses have already been performed by Truit et al. In 2015 and by Vallet et al. In 2014. So we compare the stellar structures evolution code that they use, so Franek and Tycho. So the physics is globally the same in the three models, except that the microphysics, the abundances that you will use for the different chemical compound inside the star, and the opacity are quite different. So here you will have a very strong impact of this microphysics input, and still you produce something that is quite similar in the three stellar code. Most notably during the main sequence phase where the planet will stay the longest amount of time. Okay, so the first take-home message is that when you want to estimate the habitable zone of a star, then you can use your favorite habitable zone prescription and stellar model. Okay, but use star level. This is the best one. About the stellar mass, so here we compare the effect of a change of stellar mass on the evolution at the habitable zone. Here this is for the inner edge of the habitable zone. This is the same result for the outer edge. And as you can see here, with a slightly change of 0.1 solar masses, you have a tremendous effect in the habitable zone limits. So here, when you estimate for the observer, when you estimate the habitable zone limits, the mass is crucial. You need a very good estimation of the mass of your object, because here the stellar mass is model dependent. So you will get the effective temperatures and luminosity from the observation, but then you will use isochrone given the age of your system to get the evolution of your star. So if you pick the wrong mass, then you will completely shift the habitable zone limits, and maybe your planet will not be in the habitable zone or be in the habitable zone instead of being outside or inside. This is the same effect for the metallicity. A slight change of metallicity will have dramatic effect on the habitable zone limits. So here again, metallicity is very crucial. You have to very well estimate this quantity. So the take-home message, of course, the second take-home message is that for observer, when you use stellar models to estimate the habitable zone limits, you need a precise estimation of the mass of your star and the metallicity of your star. And finally, stellar rotation and stellar activity. So here we compare the impact of the rotation on the evolution of the habitable zone limits. So here this is the slow rotators, median and fast one, 3.6 stellar angular velocity and 18 stellar angular velocity, solar angular velocity, sorry. This comes from the observed distribution of the Orion Nebula cluster at 1 billion years, so we scale it to observed trend. And as you can see, the rotation have very small impact on the habitable zone limit, except at the zero-age main sequence, where you will find the most impact of the rotation that is correspond to the end of the contraction phase of the star. So during the permanent sequence, the star is contracting before reaching the zero-age main sequence, where eventually the nuclear reaction will be initiated. So during that phase, your contraction, so you reach the maximum rotation rate for your star. So this is where you have the most extreme impact of the rotation, and still you almost see no impact at all. And And now, about the stellar activity that is linked to the stellar rotation. It depends on the mass, and I will focus on stellar activity. So one of the proxy of the stellar activity is what we call the Rossby number, that is defined by the ratio of the inertial to Coriolis forces. We can express it more simplified version as a ratio of the surface rotation period of the star to the convective turnover timescale, where the convective turnover timescale is the time it takes for a convective eddy inside the convective envelope of the star to perform one revolution. So if the Rossby number is lower than 1, it traces high stellar activity, while Rossby number over unity traces no or small stellar activity. This figure here shows the S-Prong-Russell diagram of a 0.31 and 2 solar mass star. So this is the luminosity as a function of the effective temperatures. And here we color-coded the evolution of the Rossby number during all the evolution. This is for the inner edge and outer edge of the habitable zone. So what we found is that there is a high stellar activity during the early permanent sequence phase. The permanent sequence is here. Then you have the main sequence. This is the 0.31, 2 solar masses. So you have the permanent sequence here, main sequence that starts here, and then you reach the subsession phase. And as you can see here, there is a high stellar activity during the early stage of the permanent sequence phase, where the habitable zone are the closest from the star. So here it may have a strong impact on the early phase of the life development and life complexification. So we can ask the question of magnetic protection. And what is the minimum magnetic field that is required for a planet for an efficient magnetic protection? Here we use the work of Aline Vidotto 2013 that expressed this minimum magnetic field as a function of the magnetic field strength of the star and as a function of the square ratio of the radius of the star and the orbital distance of the planet. Okay, so basically what they do, that they look at the impact of stellar activity and mass loss rate on the atmosphere of a planet, and they look at the magnetosphere, and so thus the planetary magnetic field that you need to protect your atmosphere. To express the magnetic field strength of the star, we use the observed strength get by Colin Folsom et al. In 2016, where they performed polarimetric analysis to get the mean magnetic field strength of the star. Here they compiled 3 different surveys, the 2P, Becool, and MAP project, and they found a correlation between the mean magnetic field and the Rossby number that has the magnetic field that evolves as the inverse of the Rossby number. We included it in StarEvol to get the evolution of the minimum magnetic field that is required for an efficient magnetic protection as a function of age. So with this figure here, we start at the 0th order to constrain the planetary habitability. And note that with this observed trend, we still reproduce the order of magnitude of the Sun and Earth magnetic field. But here, this figure is produced using a planet that is fixed at 1 AU, so no evolution of the orbital radius of the planet. So what about orbital evolution and tides? This figure here summarizes how tides work, so in an easy way. So let's say that you have a star and a planet. So the star will see the potential energy of your planet, the tidal potential that will be transferred into kinetic energy inside the star through the tidal flows and the displacement. And then this kinetic energy will be converted into the system evolution, like evolution of the spin and the orbital property of the planet, as well as a modification of the internal structures of the star through the tidal heating. And this conversion is done through what we call the tidal quality factor, that is an estimation of the response of a given object to tidal distortion. And this quality factor strongly depends on the internal structures of the star or the planet, but here we are looking only the case of a star, so it depends on the internal structure of the star and depends on the dissipative processes that are involved in the star. Okay, So the question are, what are these dissipation processes that convert this kinetic energy into thermic one that will affect the system evolution and the internal structures of the star? And what is their dependence on the structures and excitation frequency? In study of star planet system, the body, star and planet, are often assumed to be point mass object, especially for the planet, compared to the relative size of the two, or solid body. Okay, and we used ad hoc prescription to add the tides, stellar wind, magnetic interaction to evolve the rotation of the star, for instance. But the bodies, planets and stars, of course, harbor complex internal structures that should be taken into account in such analysis. So here we clearly need of an ab initio physical modeling. The problem is that the tidal interaction formalism is very heavy, so it's very hard to implement it in stellar structures evolution model or orbital evolution code. The dissipation spectra here, as you can see, are very complex and depend on the stellar mass, the rotation, and of course evolve as a function of time. So what we need here is an order of magnitude of the tidal dissipation along the stellar evolution. And for this we use the frequency average tidal dissipation from Ogilvy 2013 and Mattes 2015 that express this dissipation as a function of the internal structures of the star and as a function of the rotation rate. So here for the structures, it depends on two quantities, alpha and beta, that are the aspect and mass ratio of the star, so the relative size and mass of the radiative core compared to the whole star, and the rotation through the critical velocity and the surface rotation rate of the star. So this is what we get when we had this frequency average tidal dissipation inside the stellar structures evolution called star evol. So this is what we call the tidal Espring-Rochelle diagram. So you have beta, the mass ratio, and here alpha, the aspect ratio. And we put here the evolution of stars between 0.3 and 1.4 solar masses along this plot. And as you can see here, first you start with, this is the color coded is the dissipation, okay? So white you have the maximum of the dissipation, and blue you have the minimum of dissipation. Okay, so you start here with minimum dissipation, there is no core, so this and this are 0. Then you evolve, you start your core growth, you pay through this maximum islet in this plot. This is the pre-main sequence here. You reach the main sequence where you will stay 4 billion years, so most of the evolution will be there. And then you move to the subgiant phase where you increase again the dissipation, move close to the maximum, and then up you move through lower dissipation. So as you can see here, there is a variation of the dissipation and of course of the tidal quality factor, that is the inverse of the dissipation. There is a variation over several orders of magnitude of this quantity as a function of the mass. Here you have the amplitude of the tidal quality factor that increase during the main sequence with the stellar mass, okay? Here you have the pre-main sequence, the main sequence, the subgiant phase. So as you can see, this figure here shows the tidal quality factor as a function of age for the structural evolution only. So there is no evolution of the rotation rate of the star. So this is just to check the impact of the internal structures on this quality factor. So you have something that is quite flat here, depends on mass. And when you add the rotational evolution, as you can see, it changes everything, okay? So here, during the pre-main sequence evolution, there's something that is quite similar because the rotation is controlled by the evolution of the internal structures of the star during the pre-main sequence because of the contraction. While during the main sequence, this is the stellar rotation that controls everything. So you have very huge impact of this rotation on the tidal quality factor and thus on the tidal dissipation of your star, okay? And one of the striking recent examples is the work of Emmeline Baldwin and Florian Mattes, 2016, that look at the evolution of the semi-major axis of different star-planet systems. Here, this is the results for a 10 Earth mass planet orbiting a 1 solar mass star. You have the evolution of the semi-major axis, evolution of the rotation rate, and evolution of the dissipation. Here, they consider different initial semi-major axes. The dashed line here are what they get with the standard tides model, so with a constant quality factor over the whole stellar evolution, while the solid line are for the new model, okay? And as you can see here, when you use the standard tide models, nothing happens. The planets stay at the same location for the whole stellar history, except at the end, where you start to see something, but not much. But when you use this new average dissipation, frequency average tidal dissipation, then everything changed, okay? You have outward migration for some of the case here. You have inward migration and even the planet that fall into the star. So this changed everything, okay? This is very interesting. But these results are for a non-rotating stellar model, okay? To get standard model from the literatures, and they put ad hoc stellar rotation prescription to evolve the evolution of the angular velocity of the star, okay? But we know that the tides will both affect the rotation of the star and the internal structures. So we need to include a real retraction of the rotation on the internal structures due to tides. And this is exactly what I'm trying to do. Sorry, I don't have any results yet, but I'm trying to couple the star-evolved model, so the stellar structures evolution model, to Mercury T, used by Emmeline Baldwin, that is a dynamical orbital evolution code, to get the impact of the tides on the rotation and on the structures of the star, as well as the impact of the tides on the planetary migration, okay? So this is a collaboration with Emmeline Baldwin and Florian Mattes, and with this, we will be able to constrain to constrain furthermore the planetary habitability, okay? I also plan to provide the community with the stellar grid for the habitable zone evolution that I'd show you, and also the grid of tidal dissipation and tidal quality factor that we get with this new prescription. I also want to acknowledge that I am developing online tool to easily get the main features of the habitable zone. So you can choose your star, you can choose, you can put your favorite planet at your favorite age, use different prescription for the habitable zone, and check if your planet is inside the habitable zone or not. So please visit the website and send me your feedback, advice, and comment what you want, what you need, what you don't like. And I will be glad to get your feedback. That's it. Thank you.